Can you see me? As you can see, we have 150 dice here. Okay, this is my setup to film all the dice. The iPad camera is pretty shitty. Maybe I refilm that with the iPhone. So that's my camera setup. Hey, for the dice experiment. And so I bought 1,000 dice on Temu, but we can't use 1,000 actually. But we'll try to use as many dice in one throw as possible. As you can see, we have 150 dice here, because that's 10 dice. 10 times 3 is 30, and 30 times 5 is 150. Okay, and we'll be using 150 dice to make the experiment. Oh yes, all of you, go in here. So, this is what the first roll will be looking like, and we'll be taking a picture of the result. So, first roll. Okay, I think that's well countable. So I'll be taking a picture. So I will explain how this algorithm works. First of all, we have a folder with 100 images, and each image captures the state of a roll of 150 dice. One image, 150 dice. So we have 150 results per image. That means one row, 10 images. That is 1,500 individual results of a dice roll. And because we have 10 rows, that's 15,000 results. And the pips is the numbers that a dice shows. So what does my algorithm do? We have two important files. This one takes all those images and analyzes them with a function that I'm about to show and explain. Holy shit. Alright, so here's the new repository, and here come the analyzed images. Such an image looks like this then. Depending on how many pips are on the dice, it is colored, and the number of pips is shown in round brackets. Yeah, all those images are classified. Can go into a random image, 3, 6, 3, 5, 2, and all of those results are being computed together, counted, and put into a global statistic. So we can see how many 1s, 2s, 3s, 4s, 5s, and 6s. 6s have been rolled by the dice. So, okay, about 80% done, 80 images have been analyzed. We are about to wait for the final 5 images, and then I'm about to show you how I did it, how the algorithm actually can recognize the number of pips on a dice. Okay, this is, by the way, our final statistic, a so-called histogram, a visualized statistic. So, as you can see, all results are between around 2,300 and for 15,000 rolls, between 2,300 and 2,600, which makes a lot of sense, because if you divide 15,000 by 6, that would give you 2,500. So the average of pips is also 3.5. I wanted to see if maybe theory doesn't hold here, mathematical theory, but as we can see, it does hold. Why is the average 3.5? It always helps to visualize stuff. I will show that. Quick and dirty. We have our dice. Results between 1 and 6. What is the average? Why is the average 3.5? Well, if we go exactly in the middle, here, that is exactly the middle. This is between 1 and 6. It's 3.5. This is why the average between all dice rolls is 3.5. Like, by the way, we can see total dice that have been analyzed is 15,000. Again, how did we get, for example, this? Such a cool image where we recognize the number of pips on a dice. Well, it works like this. This is the magic function, and we will step through it now. For people who have never seen it, that may be interesting. So I will show the example of this picture, how this gets analyzed. First of all, we load the image with CV2, that means computer vision 2. It's just a collection of a lot of computer code with which you can analyze images. We load the image in BGR because an image consists of pixels, and each pixel has 3 so-called channels. Usually it's RGB, red, green and blue. Red, green and blue. Those 3 channels. CV2, computer vision 2, uses BGR, blue, green, red. We load the image, which has, I think, 12.2 million pixels. But we load the image. So this takes a lot of time. We load the chunks, containing probably some 100,000 pixels, tens of thousands of pixels, and it should open up this sidebar. Here, perfect. We can see, if we zoom in into the image, then you see this is just a lot of single pixels. And each pixel has 3 values. We said that before. Blue, green and red. So 235 is the blue value, 249 is the green value, and 255 is the red value here. Now, to simplify and make the analysis quicker, we take all 3 values and calculate them into a single grayscale value, meaning we either have black, gray or white, but not arbitrary colors anymore. Here we have 3 values, as you can see, 28, 35, 44 or so, and here we only have one single value per pixel. Now, to even further simplify this, we will say, okay, each image either has black 0 or white 255 as a value. And then we get this dice mask. And the dice mask, it loads much quicker because we only have 2 values, either black or white. As you can see, a pixel is black and here it's white, 255, black, white. Okay, black, white. The pips are also black. Now, after we've done this, we go over this image and say, okay, where is a chunk of coherent white pixels that are in a square form and is sufficiently large enough to say this is a dice. Let's jump into the function which actually counts the number of pips, because now that we have correctly analyzed 150 white coherent contours, we want to know how many pips are in each single contour. So we take a single die that looks like this, a die. We invert actually the white and black to arrive at something called the pip mask. What can you see here? You can see the pips are not black anymore, they are white now. That makes it easier for the algorithm to recognize, okay, here we have a coherent circle of white pixels. It is roughly round. This must be a pip. Here is also a coherent area of white pixels, but this is by far not round. It's super long and super, like, the height is very tiny and small. Therefore, this cannot be a pip. The algorithm does that for every dice. And here it will obviously find 5 pips. That's basically how the algorithm works. And then, as you could see, we have a lot of analyzed images and a nice statistic. That's how it works, guys. Cheers.